So this video will go very fast because this is not something that I expect people to follow at a very, very close level, but I at least want to show you an example. So inevitably, some of you are going to ask me if something like this can be on the exam. Of course, if I cover it, it could be on the exam, but I'm not going to beat you up too hard on this because it is explicitly ordinary differential equations, which, again, not all of you have had and not all of you will take. So I just want to show you that this differential equation is something that you all solved in Calc 1. To solve a differential equation, you're looking for a function that satisfies both of these rules. This is called the initial condition, and this is the differential equation itself. So I'm looking for a function, y of t, that satisfies the property that its derivative is a constant times itself. And then at 0, I need to have the property that it has some prescribed value, which we'll call y naught. This differential equation describes exponential growth and decay. So if this constant is positive, then this is an exponential growth model. You can think about something like population or some sort of investment with an interest rate. And if a is less than 0, this represents decay, which is what the markets are doing now. So the unique solution to this initial value problem is y of t equals e to the at y naught. So this is the solution, and I've written it in this way for a particular demonstrative property. So the solution is e to the at y naught, and you can verify, and you should do this. When you plug in t equals 0, you get y naught, check. And when you differentiate this, this is just a constant, so the chain rule will pop out an a, and so the derivative of y is a times the thing you started with, which is exactly what this differential equation says. So in ODEs, there are higher order systems, and I chose one that looks like a mass spring system or a circuit system, LRC system. And so you can write it in this way. So the dots here represent time derivatives. So this is 2 time derivatives, 1 time derivative, and no time derivatives. And then this function over here is called a forcing function. So this is a second order linear constant coefficient ODE. It's non-homogeneous. And since it's second order, we have 2 initial conditions. So if you didn't follow all that, that's okay. But the point is that this arises in a huge class of physical problems describing mechanics, describing things involving energy, describing all sorts of things as circuits, as I mentioned before. So what I want to show you is that you can use linear algebra to convert this problem into one that looks like this. And the reason why you might want to do that is, as you might imagine, and you would be correct, second order or third order or fourth order problems are intrinsically more complicated than first order problems. So if you can find a way to make this look like this, then you're golden. So this procedure is called the method of reduction of order. In fact, this is something I'm covering in ODEs right now. So if you start with a vector y, and this y has 2 components, y and y dot, then you can rewrite this system in the following way. If you take the derivative of this vector y, that means taking the derivative of each component. So y becomes y dot, and y dot becomes y double dot. So the derivative of the first derivative is the second derivative. Then y dot, of course, is equal to y dot. That's just a tautology. And y double dot is equal to, just rearrange this. So you have f on the right-hand side, and you do minus dy, you do minus k. So you just subtract off. And so here's the thing which you're not going to see, obviously. It's not going to be clear, but you can check, is that y dot equals this can be written in terms of a matrix. So what I'm going to do is I'm going to ask you to check this. So pause the video if you want, and check to see that if you take y and you replace it by y and y dot, and you apply this matrix to this vector, what you'll get, and then add this, what you'll get is exactly what we have here. What we have here is exactly what's expressed in this system. So this is called reduction of order because we started with a second order system in a scalar variable y, and we've ended up with a first order system in a vector variable y with the hat. And so what this motivates is the ability to study first order systems where the derivative is being applied to some vector. So this is a 2x2 system. And so I just wrote down here, how might we solve, or how might we capture such a system? Well, let A be some n by n matrix, let y be an n by 1 vector, and we can always consider, this is the homogeneous problem, so I've taken f to be 0. We can always consider y dot equals ay, and our initial state, or our initial condition, is just some vector in Rn. And so notice, and some of you have probably already wandered down here to see what the solution is, but notice this vector system, this vector system, looks exactly like this thing from Calc 1, which all of you have solved, right? Y dot equals AY, Y of 0 equals Y naught. Y dot equals AY, Y of 0 equals Y naught. Now here, things are vectors, so I think it's a little bit more complicated, but the solution is still e to the at Y naught, and the reason is the same. If you plug in t equals 0, this gives you the identity matrix. The identity matrix times Y naught is Y naught, and that satisfies this initial condition. If you differentiate this thing, right, take d dt, the same rule applies that you've known forever, which is that the chain rule will bring this constant down. In this case, the constant is a matrix, so this will be a e to the at Y naught, and that means that the first derivative of y is in fact a, the matrix A, times y, the thing you started with. So what you're seeing here is that the solution to this nth order linear homogeneous differential equation is in fact e to the at Y naught, and this is true for any matrix A. So you can get away with a diagonal matrix, a non-diagonal matrix, a diagonalizable matrix. The solution is always just e to the at times the initial condition, but the challenge is how to compute e to the at. And what I want to point out is this is exactly what we were talking about in the previous video. So as long as A, the matrix A, is diagonalizable, and we know that that corresponds to having n linearly independent eigenvectors, as long as it's diagonalizable, I can do this. So e to the at is just p dt, e to the p dt p inverse. So if I just throw a little t in here, that would be e to the at. So anytime that the matrix A is diagonalizable, right, then I should have a nice mechanism for computing e to the at, which I want to do now. Okay, so let's start with a simple case, not where it's diagonalizable, but where it's diagonal. So e to the, so d is diagonal, so a, j, j are the entries. Then e to the dt is just the diagonal that has e to the entries with a little t thrown in there. So I did one here. If d is this diagonal matrix, then when I compute e to the dt, I'm just putting on the diagonal e to the 3t, e to the minus t. It just works that simply. And this is exactly the rule that you saw up here from the previous video. So e to the dt is e to the a11t, e to the a22t, and in general it's diag e to the ajjt, which is exactly what you see down here. Okay, so now let's do an example when the matrix is diagonalizable. So again, e to the at, using the rule that we had up here, right? E to the at is e to the p dt p inverse, which is p e to the dt p inverse. So if I come back here, that's exactly what I wrote out. So e to the at is p diag e to the j ajjt p inverse. So if I wanted to compute a solution to a differential equation with a diagonalizable matrix, this is what I would get. So I wanted to do that. So this is not a diagonal matrix because it has an entry up here, although it is upper triangular. So I want to solve this ODE system. Now, I didn't specify the initial condition, but that's okay. The initial condition will just be written as y naught. So I'm going to start to solve this, and this is a skill I would like you to have, is to identify that when you see this differential equation, the solution should be e to the at, and to compute e to the at, you're going to need to use this rule for diagonalization, which means as a starting point, you need to diagonalize. So when you diagonalize, you're going to compute the eigenvalues. In this case, the eigenvalues are 2 and 3. Once you have the eigenvalues, you're going to compute the corresponding eigenvectors. And I just wrote out here, for lambda equals 2, you subtract 2 off the diagonal. That leads to this matrix, which gives you this augmented system. You solve for the eigenvectors, which are in this case a one-dimensional subspace. S here is a parameter. And if you want, you can choose the eigenvector to be the vector 1, 0. So this is the eigenvector 1, 0, choosing s equals 1. For this eigenvalue, lambda equals 3, you compute a minus lambda I. You solve this augmented system. It gives you the eigenvector minus ss. If you choose s equals 1, you get minus 1, 1. So the eigenvector corresponding to the eigenvalue 2 is this vector 1, 0 in the first column, and the eigenvector corresponding to this eigenvalue 3 is the vector minus 1, 1 in the second column. And so when you diagonalize this matrix A, when you diagonalize it, you would get P, D, and then P inverse, which I did not compute. And when you exponentiate, following the rule that we have above in this video, you will get P e to the d p inverse. And so as long as you've specified what p is and what d is, then the matrix exponential e to the at, where this is a, is in fact equal to p e to the dt, p inverse applied to y naught. So this is the solution to this differential equation. And at that point, if as long as you've specified what D and P are, then this is a viable answer. So I'll try to give you one or two questions in the homework that are like this, just so that you can practice once or twice.